Welcome to the Center for Safety, Equity, and Transportation's March webinar. The webinar today is Deep Learning-Based Applications on Intelligent Transportation Systems using Light Detection and Ranging, or LiDAR technology. Dr. Shanglian Zhou is a postdoctoral research fellow in the Department of Civil and Environmental Engineering at the University of Hawaii, Manoa. His research interests include vision and vibration-based health monitoring of civil and transportation infrastructures through deep learning and smart sensing. And he will be speaking to us today about his work with LiDAR. And with that, I'm going to hand it over to Dr. Zhou. Go ahead, Shanglian.
Thank you, Vicky. First of all, I would like to introduce my co-authors and colleagues who contributed to our research. They are Dr. Hao Xu from University of Nevada, Reno, Dr. Guohui Zhang from University of Hawaii at Manoa, Dr. Tianwei Ma from Texas A&M University Corpus Christi, and Dr. Yin Yang from the University of Utah. In this webinar, I'm going to cover the following topics. The first section introduces the characteristics of LiDAR data. Then I'm going to introduce some recent work by our research group, which have focused on deep learning-based applications using LiDAR data. The last section summarizes the research findings and concluding remarks. In recent years, light detection and ranging technology has been extensively adopted for environmental perception tasks in transportation research, including land surveying, autonomous vehicles, traffic big data, traffic object recognition, etc. As a remote sensing method, LiDAR sensor utilizes laser pulses for 3D distance measurement. Compared to traditional data acquisition devices, such as cameras, LiDAR sensors have the advantages of high precision distance measurement, fast data acquisition, and a wide detection range. Besides, unlike image data, LiDAR data are not sensitive to varying lighting conditions. Thus, LiDAR sensors can be deployed for nighttime data acquisition. On the right-hand side is an example of the Velodyne VLP32C LiDAR sensor that we have been using for research. The LiDAR sensor has multiple channels of infrared laser emitters aligned vertically to cover a 40-degree vertical field of view. The laser pulse can be reflected and received up to 200 meters with an accuracy of ±3 centimeters. Now, when each infrared laser emits a laser pulse, its time of shooting and direction are registered. The laser pulse travels through air until it hits an obstacle, which reflects some of the energy. A portion of that energy is received by the paired infrared detector, which registers the time of acquisition. Then, based on the difference between the time of acquisition and the time of shooting, the distance can be calculated. During data acquisition, the LiDAR sensor rotates around the vertical axis. Thus, the laser beam can cover a 360-degree horizontal field of view. Now, this figure is the bird's-eye view of the LiDAR sensor. Depending on the rotational speed, the horizontal resolution can be from 0.1 degree to 0.4 degrees. This is an example from YouTube, which visualizes the LiDAR data captured in autonomous driving scenarios. The LiDAR sensor is installed on a survey vehicle to capture 3D point cloud LiDAR data of the surroundings. In this video, the adopted LiDAR sensor has 64 channels. The circles on the ground represent the reflected laser pulses from each laser channel. You can see that the surrounding vehicles and pedestrians are all captured in the form of point clusters. Unlike a 2D image in which each pixel corresponds to a row and a column index. A LiDAR point cloud is unorganized because the coordinates of each point are in a continuous domain. Another characteristic is that LiDAR data point clouds are non-uniformly distributed. Because the laser pulse travels in a straight line, the obtained point cloud has a lower point density at a farther distance, as shown by the figure on the right. In order to process LiDAR data for object recognition tasks, LiDAR point clouds are often transformed into 3D voxels or 2D pseudo images. Existing methods often choose to convert 3D LiDAR point clouds into 2D pseudo images to take advantage of computer vision and deep learning based techniques such as convolutional neural networks. Now, one of the popular approaches is that to convert LiDAR data into front view representation, where the point cloud is transformed into a 2D matrix, with each column representing the horizontal field of view from 0 to 360 degrees, and each row representing the information obtained from each laser channel aligned along the vertical direction. Another popular approach is to transform the LiDAR data into a 2D RGB image based on a bird eye view representation. For example, the red channel refers to the depth information of each point in the point cloud. The green channel refers to the distance to the sensor, and the blue channel refers to the reflected laser intensity. Of course, there are many different ways to encode LiDAR data into 2D RGB images. This slide introduces some popular platforms for LiDAR instrumentation and data acquisition. LiDAR sensors are often installed on autonomous vehicles to capture 3D data of surrounding vehicles for autonomous driving purposes. Meanwhile, in recent years, unmanned aerial vehicles have been extensively developed and adopted. Researchers and commercial companies also tried to deploy LiDAR sensors on UAV platforms to capture aerial data for land surveying, for example. Besides, there are also infrastructure-based LiDAR sensors, such as those installed on traffic signal poles at road intersections for traffic monitoring purposes. This table briefly summarizes the differences among these three instrumentation approaches. Regarding the objects of interest, researchers focused on identifying nearby vehicles, pedestrians, and other vulnerable road users from autonomous driving data and the infrastructure-based LiDAR data. For airborne LiDAR system, the objects of interest are often buildings, land, vegetation, etc. For LiDAR sensors installed on autonomous vehicles and the UAVs, because the platforms are moving, the background in the captured LiDAR point cloud will move accordingly. In contrast, for infrastructure-based LiDAR, such as those installed on traffic signal poles, background is stationary. Researchers often use autonomous driving LiDAR data to detect nearby vehicles and pedestrians, and meanwhile identify their related motion patterns. Meanwhile, for the LiDAR sensors installed on UAV platforms, because they are capturing data from a higher elevation, the covered detection range is larger, along with a lower resolution. For infrastructure-based LiDAR, they are often deployed on traffic signal poles in order to cover a wide detection range, focusing on capturing traffic objects at different distances. In the literature, many large-scale LiDAR datasets are captured from autonomous driving scenarios and made available to the public. For example, the famous semantic kitty LiDAR dataset provides a large-scale dataset labeled for semantic segmentation tasks. Semantic segmentation is the process of identifying the category of each point in a point cloud. The semantic kitty dataset contains 28 different classes. In this figure, different colors represent different classes. Another popular dataset is the nuisance dataset, which contains both LiDAR and image data for 3D object annotations. The nuisance dataset has both semantic label and vehicle bounding box label, and contains 32 different classes for deep learning training purposes. Similarly, The Waymo open dataset contains both LiDAR and image data for 3D object annotations and has both semantic labels and bounding box labels for 23 classes. All of these datasets are very good resources for training deep learning models for autonomous driving purposes. Of course, there are many other publicly available large-scale LiDAR datasets developed for LiDAR-based deep learning research. This slide briefly introduces some common issues existing in LiDAR data. The issue of occlusion can occur when the background object is blocked by a foreground object, as shown in this video. As we can see, the pedestrian objects and the background are sometimes partially or fully occluded by nearby vehicle objects. In transportation research and applications using LiDAR data, it remains a challenge to achieve consistent feature recognition and extraction from occluded LiDAR point clouds. Another common issue is the influence from severe weather conditions, such as rain, snow, and fog. For example, tiny snow particles can easily backscatter laser beams and show as scatter points in the center of the point cloud, as demonstrated by this figure. In fact, many researchers have reported that the quality of LiDAR data captured in snowy or foggy weather is usually deteriorated. In the next section, I'm going to introduce the issue of snow disturbance in further details and describe the filtering technique that we developed for noise removal. The first research topic is denoise LiDAR data corrupted by snow noises. As mentioned earlier, the impact of severe weather conditions can affect quality of LiDAR data by creating noises in the captured point cloud. Well, one of the typical noises introduced by severe weather is snow noise. Because snow particles have a similar dimension as the wavelength of the infrared laser pulses, which is around 900 nanometers. The snow particles can easily backscatter laser beams. As a result, in the captured point cloud, the snow particles will show themselves as solid diffusing objects that disperse around the sensor location, as shown by the figure on the right. Such snow noises need to be eliminated before the LiDAR data can be used for further analysis. However, existing general-purpose noise removal methods are more focused on smoothing 3D surfaces, and their performance on 3D LiDAR data is very poor because they are not specifically designed to account for the unique characteristics of LiDAR data, such as the non-uniform distribution of LiDAR point clouds. In this research, we developed a filtering technique called dynamic channel-wise outlier removal filter. It has two key features. First of all, unlike the existing methods, which usually process the entire LiDAR point cloud in a consistent manner, the proposed filter chooses to process the LiDAR data channel by channel. By doing so, the snow outliers can be decoupled effectively based on different laser channels, and the data dimensionality and complexity can be effectively reduced along the vertical direction. The second feature is that the proposed method employs a dynamic search radius to search for neighboring points, as illustrated by the sketch on the right-hand side. As we mentioned previously, when the distance to sensor increases, the point density will reduce correspondingly. Basically, the proposed method utilizes a larger search radius at a farther distance to account for the non-uniform distribution of LiDAR data. To be specific, the proposed method contains two hyperparameters. The first one is called the distance factor, which defines the ratio between the dynamic search radius for a point and the distance between that point to the LiDAR sensor. Therefore, the search radius is proportional to the distance and can be dynamically adjusted. The other hyperparameter defines a minimum threshold on the number of neighboring points. The idea is, if the number of neighboring points within a search radius is fewer than the threshold, then it means the point is more likely to be an isolated point, and therefore is marked as an outlier. In the experimental study, the Velodyne VLP32C LiDAR sensor was adopted for data acquisition. This sensor covers a 40-degree vertical field view and a 360-degree horizontal field of view through rotation. The LiDAR sensor was installed on a traffic signal pole at a road intersection in Reno, Nevada, as shown by this figure. Data acquisition was performed under severe snow weather, and the obtained LiDAR data are all corrupted by snow noises. As previously mentioned, the proposed method involves two hyperparameters. The distance factor controls the dynamic search radius, and the minimum number of points determines the threshold on the neighboring point. In order to obtain the optimal hyperparameter values, we performed an optimization through grid search by exploring different combinations of the two hyperparameters. The performance on noise removal is measured by the F1 score, and the result is illustrated by the figure on the right-hand side. In this figure, the X and the Y coordinates, the X and the Y axis are the two hyperparameters, respectively, and the Z axis refers to the F1 score. The blue dots represent the sample points that correspond to different hyperparameter combinations. The green dot refers to the optimal hyperparameter value. Meanwhile, a 3D surface is fed to the data to show the trend. We can observe that the distance factor has a larger impact on the performance, and in contrast, the threshold on the neighboring point seems to have little influence. And the optimal hyperparameter we obtained as follows. The performance on snow removal is further demonstrated through this video. In this video, the figure on the left visualizes the raw LiDAR point cloud under snow disturbances, and the right figure shows the filtered point cloud by the proposed method. We can clearly see that the proposed method can effectively and consistently eliminate the snow noises, while the vehicle cluster is preserved. Okay. Furthermore, we compared the proposed method against other existing methods, including two state-of-the-art methods and two general-purpose methods in terms of their performance on snow removal. Judging from the plot of the F1 score, we can see that the proposed method achieves the highest F1 score, indicating the best performance. From the graphical results on the right-hand side, the proposed method and the DSOR filter both can effectively eliminate the snow noises that exist in the center of the point cloud. However, the other methods result in some remnant snow noises, especially for the general purpose methods. Beginning from this slide, I'm going to introduce the second research topic, which is focused on deep learning-based vehicle bounding box detection using both autonomous driving data and the roadside LiDAR data. As we introduced previously, there are many publicly available large-scale LiDAR datasets from autonomous driving scenarios. Researchers often employ these autonomous driving LiDAR data for deep learning model training and testing. However, for infrastructure-based LiDAR applications, such as deep learning-based vehicle bounding box detection from roadside LiDAR data, a publicly large-scale roadside LiDAR dataset is lacking. As a result, researchers often need to collect their own data and generate ground truth labels for network training, which is extremely time-consuming and labor-intensive. Although roadside LiDAR are different than autonomous driving LiDAR based on their different instrumentation and data acquisition approaches, there are several similarities between these two types of LiDAR data. For example, the general shapes of vehicle objects as well as their motion patterns are similar. Therefore, in this research, we focus on exploring the feasibility and the challenge of transferring the learned knowledge from autonomous driving LiDAR data to detecting vehicle objects from roadside LiDAR data. This slide illustrates the deep convolutional neural network we developed for vehicle bounding box detection. The proposed network is modified from the from point pillars, which is an established network for 3D object detection using 2D convolutional layers. In order to take advantage of the 2D convolutional neural networks, the 3D LiDAR data are transformed into studio images based on a bird's-eye view representation. Furthermore, we employ the dense connection modules as shown by the green blocks for more comprehensive feature extraction. Unlike the traditional linear connectivity patterns, the dense connection encourages feature reuse by taking the information from all the preceding layers as the input. This figure shows the flowchart of the proposed deep learning-based method. The first step is to collect roadside LiDAR data. Then the proposed network is trained and tested using a publicly available autonomous driving dataset. In the next step, we directly leverage the deep convolutional neural network trained on the autonomous driving dataset to detect vehicles from the roadside LiDAR data as a practice of knowledge transfer. In the experimental study, the Panda set was adopted for network training and testing, which is a popular autonomous driving dataset with bounding box labels. The LiDAR data in the Panda set were collected using a 64-channel LiDAR sensor. An example of the LiDAR point clouds and the bounding box labels is shown by the figure on the right. Meanwhile, roadside LiDAR data were collected from a road intersection in Reno, Nevada, by installing a 32-channel LiDAR sensor on a traffic signal pole. An example of the captured LiDAR data is shown by the figure on the bottom right. By comparing these two figures, we can already see the difference in terms of the point density, which is caused by the different number of laser channels. This slide shows the bar plots of the testing results measured in precision, recall, and F1 score. The figure on the left is the testing result on the autonomous driving LiDAR dataset. Judging by the F1 score, which is the comprehensive measure, we can conclude that the proposed network outperforms the other two networks, namely the original point pillars and the YOLO V4. And all the three networks yield good performance on detecting vehicles from the autonomous driving data. Meanwhile, the figure on the right is the testing result on the roadside LiDAR data. Similarly, the proposed network yields the highest F1 score, indicating the best performance. Nevertheless, as shown by the red dashed lines, by directly applying the networks trained on autonomous driving LiDAR dataset to process roadside LiDAR data, their overall performance will drop, which is caused by the differences in their data characteristics. An example of the detection results is provided here. From left to right shows the results by point pillars, YOLO V4, and the proposed network. As we can see, both the point pillars and YOLO V4 yield some false negative detections and false positive detections, while the proposed network shows better performance without those false detections. The third topic is deep learning-based pedestrian trajectory prediction. Vulnerable road users, such as pedestrians, cyclists, motorcyclists, and people using wheelchairs or scooters, are subject to a risk of collision with nearby vehicles. To improve the safety of autonomous vehicles, it is very important to identify and track vulnerable road users in a prompt and accurate manner. In the literature, substantial research efforts have been devoted to predicting the motion of pedestrians and their interactions with vehicles. Nevertheless, it remains a difficult task to interpret the pedestrian crossing behavior and collision risks due to multiple factors, such as the complexity in vehicle-pedestrian interaction, the variability of pedestrian motion patterns, and the impact from the traffic signal time. Despite that, many deep learning-based methods were developed. They did not incorporate risk assessment and signal timing information into their deep learning network formulation. In this research, we propose a long short-term memory network for pedestrian trajectory prediction and risk assessment. The LSTM network is a variant of recurrent neural networks for time series prediction. LSTM is designed to address the vanishing gradient problem when processing long sequence data. As shown by the figure on the right, a basic LSTM unit consists of several gating units, including the input gate, forget gate, and output gate, which collaboratively control the information flow inside the unit. Meanwhile, the memory cell records the cell state of the previous sequence data, which remembers information over time. We proposed a multi-branch layout for adaptive feature extraction, where each branch represents a different level of complexity. The first input to the proposed LSTM network are the past the 10 steps of the pedestrian trajectories. Besides, we proposed a risk factor to assess the collision risk between each pedestrian object and its surrounding vehicles, which will be introduced in later slides. Moreover, we also incorporated the signal phasing data into our formulation because we believe the pedestrian crossing behavior is also governed by the signal timing, such as green light. The output of the LSTM network is the future pedestrian trajectory and the corresponding risk factor. Therefore, our method can not only predict the future motion of each pedestrian, but also evaluate their collision risk simultaneously. This figure is the flowchart of the proposed method. As mentioned previously, we use pedestrian trajectories extracted from LiDAR data, the signal phasing and timing data, and their risk factors as the network input. The LSTM network takes the time series data and make predictions on their future trajectories, as well as their collision risks. In the experimental study, 3 roadside LiDAR sensors were deployed for LiDAR data collection in Chattanooga, Tennessee, as shown by this figure on the right. The data are provided by the Transfer 22 competition. In the next step, both the vehicle and the pedestrian trajectory data were extracted from the raw LiDAR point clouds by Solar Robotics, a commercial company. Thus, the coordinates and the speed information can be obtained for further analysis. Regarding the signal phasing and timing data, we use the elapsed green light time or begin walk time at the intersection along both directions as the network input. The risk factor for each pedestrian is determined by 2 conditions based on the vehicle and pedestrian interaction and the pedestrian position. First, we calculate the relative position and the velocity of each vehicle to the pedestrian. If their distance is smaller than a threshold and their head-to-head speed is larger than a threshold, then we consider it a high collision risk. Second, we define an unsafe region based on a statistical analysis. As shown by the figure on the right, the majority of the pedestrian trajectories showing the green dots fall into the sidewalks and crosswalks, while a few pedestrians chose to walk on the roadways, which is considered unsafe. In this figure, the regions inside the red polygons are predefined as the unsafe region. If either of the 2 conditions are met, we consider this pedestrian behavior is at risk. The figure on the top right shows the prediction result on the X coordinate. In the scatter plot, the horizontal axis refers to the ground truth data, while the vertical axis is the predicted data. If the prediction is perfect, then all the points will fall onto the y equal to x line. In addition, the histogram of the residual is plotted as well. We can see that the method yields a high accuracy in predicting the x coordinate, where the root mean square error is between the ground truth and the predicted x coordinate is 0.225 meters. Similarly, the prediction result on the y coordinate is shown by the figure on the bottom right. The corresponding root mean square error on the y coordinate is 0.377 meters, also indicating a high accuracy. Meanwhile, the confusion matrix for the prediction result on the risk factor is provided. According to the confusion matrix, the proposed method can correctly identify the true positives, which are the high-risk behaviors. This slide shows an example of applying the proposed method on a long sequence data. On the left are the predicted x-coordinate, y-coordinate, and risk factor. The horizontal axis refers to time steps. On the right-hand side is the bird's-eye view of the pedestrian trajectory. The ground truth and the predicted data are plotted in black and red colors, respectively. From this example, we can see that the prediction matches very well with the ground truth, indicating a very high accuracy in trajectory prediction and risk assessment. The last research topic I'm going to introduce today is deep learning-based vehicle trajectory prediction and hyperparameter tuning. In the literature on vehicle trajectory prediction, the majority of existing methods are non-learning based, such as common filtering. Such methods usually require a handcrafted feature generation procedure, and the hyperparameters are often selected based on prior knowledge. More recently, deep learning-based methods such as LSTM networks were also developed for vehicle trajectory prediction. Compared to non-learning-based methods, the learning-based methods have less human intervention and user subjectivity, owing to their advantages of self-learning and adaptation. For LSTM networks, the hyperparameters can be categorized as architecture-based and training-based. The architecture-based hyperparameters, such as layer depth, control the architecture layout. Meanwhile, the training-related hyperparameters, such as learning rate, influence the network training. One of the challenges for existing methods is that they often rely on handcrafted hyperparameter selection through extensive experiments or trial and error. As a result, the user intervention and the subjectivity may still exist. In this research, we propose an optimized LSTM network for vehicle trajectory prediction through Bayesian optimization. The proposed LSTM network takes the past vehicle trajectory as the input and makes predictions on their future trajectory. Regarding the hyperparameter tuning, instead of relying on trial and error, Bayesian optimization is employed. Bayesian optimization is a global optimization algorithm for finding the optimum of black box functions that are expensive to evaluate. In our proposed method, not only the architecture-related hyperparameters, but also the training-related hyperparameters are optimized through Bayesian optimization. This slide provides a brief introduction on Bayesian optimization. Bayesian optimization has two components, a Bayesian statistical model and an acquisition function. Based on previous objective function evaluations, Bayesian optimization feeds a Gaussian regression model to the observed data and obtain the posterior predictive distribution of the objective function value at the next point to evaluate. Then, an acquisition function can be constructed depending on the posterior predictive distribution. The role of the acquisition function is to help determine the next query point through a proxy optimization to maximize the acquisition function. Unlike the original objective function, which is expensive to evaluate, the acquisition function has a closed form expression and can be cheaply sampled. The first architecture-related hyperparameter considered in the study is a layout type. We consider 4 different layout types as candidates. The first one is a linear architecture, which represents the most straightforward and popular connectivity pattern. The second layout is densely connected architecture, where the concept of dense connections were adopted to encourage feature reuse. The third layout is a multi-branch architecture, where each branch represents a different level of complexity. The network can determine which branch to use by adapting to the training data. The last one is a feature pyramid architecture, which can be considered a hybrid of the other 3 architectures. In the feature pyramid architecture, The information from each preceding LSTM layer is inherited by the subsequent LSTM layers. The layer depth is another architecture-related hyperparameter, which controls the number of LSTM layers. This figure shows an example of a three-layer multi-branch architecture. The number of hidden units is also considered in the optimization, which is determined by three factors, as indicated in the figure. For each LSTM layer, the factor A determines the variation pattern. For example, when A is equal to 0, the number of hidden layers, the number of hidden units in each LSTM layer stays the same. When A is equal to 1, it represents an ascending pattern in the number of hidden units, meaning that the subsequent LSTM layers use a larger number of hidden units. Regarding the training-related hyperparameters, both the learning rate and the momentum are updated through Bayesian optimization. The learning rate is one of the most critical factors in deep learning because it controls the convergence speed of network training. The momentum is another important hyperparameter that controls the search radius, the search direction, and accelerates the convergence. In the experimental study, roadside LiDAR data were acquired from a road intersection in Reno, Nevada. The LiDAR sensor was installed on a traffic signal pole. In total, 30 minutes LiDAR data were obtained for analysis. Vehicle trajectory data were extracted from the raw LiDAR point cloud by a common filter-based method, which was developed by our research group. The obtained vehicle trajectory data were utilized for network training and testing purposes. We used the root mean square error between the ground truth and the predicted coordinates as the objective function. And this slide shows the Bayesian optimization result. The plot in the center is the minimum objective function value plot, where the horizontal axis refers to the iteration index up to 50, and the vertical axis is the objective function value. The solid red line is the observed minimum objective function evaluations, while the blue dashed line refers to the estimate of minimum objective function value by the fitted Gaussian process regression model. Bayesian optimization was performed for 50 iterations, and the optimal case was found at the iteration 49, with the optimal hyperparameters shown on the left. In this plot, the estimate minimum objective function value matches very well with the observed minimum function objective function value, indicating a very good model fit. Meanwhile, the plot on the right-hand side illustrates the histogram of function evaluations under different hyperparameter combinations. This plot describes the exploration of the architecture-related hyperparameters, where the horizontal x-axis is the layer depth, and the horizontal y-axis is the layout type. Meanwhile, the vertical axis represents the number of function evaluations. The color of each bar represents the average value of the objective function evaluations belonging to that bar. Bayesian optimization allocates more computational resources to the combination of layer depth equal to 3 and the layout type equal to multi-branch, which is guided by the acquisition function. Also, based on the color, the average objective function value corresponding to this combination is the lowest. The figure on the left is the objective function value plot with respect to the learning rate and the momentum. Here in the plot, the horizontal axis is the learning rate, the vertical axis is the momentum. Different markers in this plot refers to different architecture layouts, and the color of each marker refers to the objective function value. Judging by the color, we can see that the objective function values are relatively low within this red circle. The figure on the right shows the objective function value plotted against the total number of learnable parameters. Bayesian optimization allocates the majority of the computational power to explore the network within the range of 10 million to 40 million parameters, as indicated by these red dashed lines. Now, with this area implies the desired model complexity to adapt to the training data. To evaluate the performance on vehicle trajectory prediction, two quantitative evaluation metrics are adopted. First one is the root mean square error between the ground truth and the predicted coordinate. In this figure, we also constructed a handcrafted LSTM network for cross-comparison purposes. As we can see, the optimal network, shown as blue color, yields a much lower root mean square error in both the X and the Y coordinates than the benchmark. The second metric is the average distance error between the ground truth and the predicted trajectories. On the right-hand side, the histograms of the average distance error by the optimal network and the handcrafted networks are plotted respectively. The histogram by the optimal network is more skewed to the left-hand side, indicating a smaller distance error. Based on these two metrics, we can conclude that the proposed method can significantly improve the prediction performance by tuning the hyperparameters through Bayesian optimization. An example of the vehicle trajectory prediction results is provided in this figure. Again, the plots on the top and the bottom correspond to the optimal network and handcrafted network, respectively. To further illustrate the detail, the result from one frame is overlaid with the LiDAR point cloud and plotted on the left-hand side. We can clearly see that the handcrafted network have difficulties in predicting the X coordinate, resulting in a large error. In contrast, the optimal LSTM network yields better performance, where the prediction matches very well with the ground truth. Furthermore, we performed a sensitivity analysis to investigate the robustness of the proposed method by creating different levels of perturbations in the optimal hyperparameter values. The perturbation levels range from 0 up to 20%, and we define the sensitivity as the change in the objective function value with respect to the absolute change in the optimal hyperparameter value. As shown by the figure on the right, it can be observed that the method is most sensitive to the change in the learning rate, showing as the blue color. Meanwhile, this plot shows the sensitivity of the proposed method is not proportional to the perturbation levels. Especially, the sensitivity value at the large perturbation levels is relatively low, demonstrating the robustness of the proposed method. In the first section of this presentation, the characteristics of LiDAR data are briefly described. And then 4 different research topics related to LiDAR data are presented. The first topic is focused on denoising LiDAR data corrupted by snow noises. We showed that our method can effectively remove the snow noises by accounting for the unique data characteristics. The second research topic is related to deep learning-based vehicle bounding box detection. Through the experimental study, we validated the feasibility of applying deep convolutional neural networks trained on autonomous driving LiDAR data to detect vehicles from roadside LiDAR data by taking advantage of the similarities in their data characteristics. In the next topic, we presented the result on deep learning-based pedestrian trajectory prediction. In the proposed LSTM network, we utilized the pedestrian trajectory data, the signal phasing data, and the risk assessment as the network input, and showed that the proposed network can achieve satisfactory performance on pedestrian trajectory prediction and the risk assessment. In the last topic, we proposed a deep learning-based method for vehicle trajectory prediction and employed Bayesian optimization for hyperparameter tuning. Not only the architecture-related, but also the training-related hyperparameters participated in the optimization. Through the experimental study, we showed that the optimal LSTM network through Bayesian optimization outperforms the handcrafted network. And the proposed method is most sensitive to the change in the learning rate value. The presentation is finished and I'm ready for questions. Thank you.
So participants, if they have questions for Dr. Zhou, can either post them in the chat, or if you raise your hand, I will enable you to speak. Enable your audio so you can be heard. Any questions? All right, I don't see any questions at this time. Oh, no, there's a question. Can from Malcolm McEwen asking, can you determine vehicle type, including the FHWA class 1 through 14 from your research?
Right now, for the deep learning model we developed, we don't discriminate between different vehicle types. So basically, for example, if there's a car and there's a truck, we consider them as vehicle. So we don't go further and distinguish their further attributes. But in the future, depending on your research needs, you can modify the deep learning model and choose to classify the vehicle into different types, of course.
All right. Any other questions? Going once. All right, well, thank you, Dr. Zhou. I'm going to stop recording now.